Um, I'm an anthropologist at Portland State University, and this is the first time I've gone to a conference or spoken at a conference where I don't know a single person, so this is an interesting experience. But I've had a very long interest in humans in space in one way or another, and that has come full circle. Of course, as a child of the 70s or 60s space race, I thought that I would go into space. That all sort of fizzled out, never happened, and I in fact went into sort of the complete, possibly opposite, which was looking into the past and into human evolution and archaeology. But now you can't sort of run away from that thing, I guess, and now I've come back to thinking about, well, I've learned a good deal now about what human evolution is, where we have been, essentially, and now I'm starting to think about how we can apply that knowledge to where we can go. And as I'll mention, I do think it's very important for humanity and civilization in particular to continue. And the way to do that, as I'll stress, is I believe, with space colonization. And I've written this book called Emigrating Beyond Earth about human adaptation in space colonization. And it's a direct approach to space colonization from an evolutionary perspective, using the lessons of evolution. Rather than in some other mode, you can approach human colonization of space from any number of channels. But I wanted to specifically begin to use what do we know from evolutionary principles that we can apply to that project. So I'll start with this is the extension from that, actually. After writing, I think there it is, Emigrating Beyond Earth, this was a rather popular title. It's popular science, a little bit more technical than popular, and the balance wasn't quite right, but a little bit more popular or technical than it should be for strict popular science. But I wanted to get some basic ideas hammered out and start to sort of get the idea out there that the anthropology or the humanities can in some way be involved in space activity. And if you go to any anthropology department pretty much in the world, I'm sure you'll find a distinct lack of interest in the distant future. And I'm starting to go after that. And in one way that I'm doing that, I'm working now with Springer to produce principles of extraterrestrial anthropology. Extraterrestrial very specifically meaning beyond Earth. Humanity beyond Earth, anthropology beyond Earth. This will be a principles or a foundations textbook, and it will go into the 4 subdivisions of anthropology, which will be physical anthropology, that's genetics, DNA, evolution, and so on, cultural anthropology, linguistics, and archaeology. And specifically look at what we can use from those to help make, again, space colonization a successful project. So a lot of the ideas that I'm going to present now have to do with my exploring these ideas. And I'm going to be dispelling, hopefully, some of the myths of what, or some of the misconceptions of what evolution tells us about where we might go. And then I'll kind of wrap up with some ideas of how we can communicate, I believe, better about humanity and about evolution with regard to its not applicability, but its humanity's, anthropology's role in trying to make this a successful project. And that, I believe, has a lot to do with how we communicate with other people about space. Most times I've gone to 100-year Starship Society conventions. I've gone to a lot of conventions dealing with space exploration. And very often, of course, they are composed, or the membership typically is composed of engineers and so on, and almost never are the humanities involved. And this is what I'm trying to start to change. So, the thoughtscape, you might say, that I'm looking at is, I need to sort of put a delineation around what am I looking at. Am I thinking about human evolution in space, on the order of 1 century, 2 centuries, 1,000 centuries? I'm starting to look at something on the order of 3 to 5 generations, maybe 150, a couple hundred years. There are a number of different reasons for this. One of the reasons for this is that I am working with the group, European group called Icarus Interstellar. They are physicists mostly, and they're working on the project to give humanity the ability to make interstellar voyaging possible at the end of this century, beginning to lay out the physics. Now, of course, many people say, no, we'll never do anything near light speed, but they're working on it. And I'm thrilled to help them with what I can do, which is the population genetics of multi-generational voyages in very unusual environments for the human genome. These are closed populations, they're small populations, and so on. So I'm starting to sketch that out. Well, I need a sort of boundary for all of that, and I'm looking at something on the order of 150 to 300 years or so, several generations. In that time period, we can see, as I mentioned, this can be, you can look at human future in space from all varieties of anthropology, the biological, the genetic, the linguistic, the cultural change, and so on. And on these time scales, you can do computer modeling. You can look at the human genome as it's been evolving already, even in recent time, and continues to evolve. And you can see that, yes, on that kind of time scale, you can see significant changes. So we can take that approach. Well, that's one of many approaches we can take. But there are also some approaches that we cannot take, I believe. And just starting to look at how evolution does work, how human evolution in particular has worked, I think we can start to dispel with some of the myths of how this is going to happen. For example, this is a diagram that was put on the back of one of my books, even though I told the publisher that they mustn't put this diagram that you always see of this, the perfect unilineal progression from a non-human primate. They're half bent over, and then they're standing, and so on. This sort of triumphant march of progress. What you don't see in that diagram, of course, is all of the lineages that didn't continue on and that became extinct. And so we need to knock that sort of thing out. For example, the march of progress, or the destiny or idea that just with the march of a sort of innate guide from the evolutionary process, or that we are somehow destined to survive in the long term and colonize space, I think those are misleading and dangerously misleading. They don't really motivate you either. And they simply are not correct. The evolutionary process, of course, produces mostly failure, and a few lineages survive. You can look at the book called Extinction by David Raup, a paleontologist, and he's the one who documents, I'm sure you've heard, about 99% of all life that has ever been on Earth became extinct. Those lineages. Most genera have a lifespan of about 20 million years. Most species about 4 million years. And extinction is common. So it's not destiny that will get us into space and survive in the long term. Hard work, that's going to be a big part of it, but that is not sufficient. We need other things as well. And what I'm thinking, or as I mentioned to you, the way that I'm leaning towards trying to make a success is essentially to copy life processes, because life processes, humans have done a tremendous amount with our inventions, but life processes really produce things that work. And the sort of guru of biomimicry, you may know, Jill Benyus, put it this way. She said that living systems or evolutionary processes have give us 3.8 billion years of field testing of every kind of design imaginable, from adhesives to things like replication, right? High fidelity replication with DNA. So what I would like to do is lean towards, all right, a life model or a life-based conception of how humanity will evolve and survive in space, and away from the, of course, we need technology, it's central, it's the way we survive, but in terms of the way that we communicate and even start to make plans, I think we should mimic as much as often, or as often as possible, mimic and learn from evolutionary ways of solving problems. Of course, evolution is not internally guided to solve problems. I think you know all that. We can give ourselves a context by looking, this is a complicated diagram, but of course across the bottom there you see a chronology, you see the origin of life, and these indicators in these black boxes with the white titles inside, these were identified by the Hungarian theoretical biologist Eor Sathmary and John Maynard Smith as the major transitions in the history of evolution. History of evolution. So compartments. Dr. Stoker was just mentioning that one of the things that happens with life is that it is segregated from other things, from non-life by membranes. Well, compartments is one of the, or compartmentalization, segregation of chemical processes essentially into early cells is an important one. I won't go over all of these. I just would like you to think about the kinds of things that are being pointed out here as major transitions. Later on, we get into eukaryotes and sexual reproduction, for example, cellular differentiation. There's a beautiful picture sent to me by Andy Knoll from Harvard University. This is embedded in a piece of stone from Australia, a cellular division about 3.5 billion years ago. Continuing on, eusocial colonies, large numbers of animals, and we start to get, of course, more data by this time, so the diagram becomes a little bit more, bit better fidelity. But basically, what I'd like you to think about is down there, number 8 is language and cultural evolution. Now, Sathmary and John Maynard Smith are theoretical biologists and paleontologists, and not interested in humanity per se. And so they're not anthropologists with the bent or a self-interest in putting humanity on the map. But it's clear from that perspective, and that I think that very long view, that humanity's evolution of language, and I'm going to propose the cultural and technological evolution that stems from that, that ranks up among the other major events in the history of evolution, or the evolution of evolution. So it's very important, and I think number 9, I have written to Sathmary now, and we'll see what he says, but I believe number 9 is going to be extraterrestrial, or movement of humans beyond Earth, and opening up, of course, effectively infinite new places for evolution, and with new methods. Other illusions that we can dispel, for example, we see that there is, of course, the illusion of design, but there are actually the results, the unintended results of these fantastic processes of evolution that can be broken down into replication of life forms, variation among those life forms, and then selection, either for or against those life forms. And of course, the astounding thing about that is it's an uncentralized process, undirected process. Certainly order does come from it, and tremendous design does come from it from our perspective. But in terms of having an internal engine that's driving it in any particular direction with any kind of intent, that is probably the hardest thing to imagine about evolution, is that it doesn't work the way that our minds work. With here is a problem, I'm going to solve it. I'm sure you're familiar with evolutionary computing that says that takes that approach and now applies it in human technology. It takes the approach of, rather than try to solve that specific problem directly, I'll begin with a swarm of attempts at solutions, and they keep iterating, and each computer cycle, they iterate a new design that is slightly different from the previous one. They're evaluated by their performance criteria for what you want to achieve, and the ones that are not doing so well are selected out. Right? That's evolutionary computing, and people use it, of course, now in even aircraft engineering. So evolutionary processes, we don't get it for free. We don't get human evolution for free. We don't get it from an internal drive. It continues, but it has to be preserved in our species or in our lineage, for example, in the primates. And very specifically, in terms of civilization, it has to be preserved. And I'll come to what I mean by civilization specifically in just a moment. If we look at our lineage, this is a beautiful painting. The original is in color from Michael Rubino in San Francisco. And this is an early primate based on the fossil and now, of course, genetic evidence. That's us about 60-odd million years ago. The beginning of our specific lineage in the mammals, the primate order, about 65 million years ago. What I mean by, a moment ago I mentioned that we don't get humanity for free. Well, what I mean by that is Mosaic evolution. Humanity, what we think of as humanity, using tools, using language, complex technology, and so on, that is a product of a number of different things that happened over a long span of time. There's no big bang. And we're finding now that even in the evolution of cognition and the evolution of the mind, there's no one moment at which it all happens. There's an evolution of memory systems, there's an evolution of recall systems, there's an evolution of activation thresholds where something was observed, a new variety of memory then allows that to be linked with something else in the thing that we now call metaphor, and this allows complex cognition. The point is, you can read older texts, and certainly this is the thing that I was brought up with. Some older texts sometimes will talk about the Big Bang of human creativity and the Big Bang of creation's sort of cognitive evolution for humanity. It's looking more and more like this. There are, of course, important events, but much more so you have Mosaic evolution. So, for example, with early humans, you have more than 4 million years ago the origins of bipedalism. And then for a long time after that, you don't have the next thing that we consider in aggregate as a hallmark of humanity, essentially, stone tool use, or the beginning of stone tool use, which will, of course, turn into starships and rovers, lunar rovers. Stone tool use and dependency, this is much later. And even long after that, on the order of several 100,000 years, encephalization, which is possessing a brain larger than you would expect for an animal of that size. Our brain is larger than we would expect, huh? For a mammal of our size. That comes later, and even for, longer after that. Increased stature, the body gets larger, and increased tissue consumption, or animal tissue consumption. And this has all kinds of effects, and I don't want to get too deep into it. But these are some of the hallmark characteristics of the origins of our genus, Homo. But they don't pop up out of nowhere. This is a product or the result of what we might call a complex adaptive system. We can identify a couple of important patterns, though. For example, early on we begin with anatomical adaptations like most other life. And there is a significant transition towards what I call the decoupling of behavior from anatomy. Here's a creature in which the anatomy severely restricts the behavioral repertoire, lacking, for example, opposable thumbs. There is a restriction to its ability to manipulate the environment. Of course, today we can manipulate individual atoms, let's say. This decoupling of behavior from anatomy is central. Begins with stone tools. Later on, we can even control processes, not just objects. And then we can aggregate all of that into these astounding things like spaceships. I'll move pretty quickly through colonization of different parts of the Earth. I think you've probably seen this kind of thing before, where people will compare the colonization of Mars, for example, or colonization of space, with other colonization efforts that have happened here on Earth. I particularly like to use ones from human prehistory. I'm a prehistorian. Prehistory, because they are even more astounding than the more recent ones, building bases in Antarctica, that kind of thing. They're even more astounding because they used even less complex technology than we have today. So, for example, we have colonization of the entire planet on the order of about 50,000 years ago. I should say, in the last 50,000 years, humanity moved from being essentially a subtropical primate to pretty much everywhere, anywhere it wanted to be. And what's really interesting about this is, although there's a little bit of body difference in types, so on the left here's an Arctic person, on the right a Nilotic person, slight different body type or phenotypic variation. Yes, there's a little bit of that, but much more important, the much more important adaptive mechanism isn't biology. We don't evolve largely by biology. We evolve by culture. And by culture, I'm including in their technology, okay, and language. That's how we've survived. And of course, a great example, you might have read Ben Finney's book, or he edited this in the 80s, and this is one of the books that I was trying to update with Emigrating Beyond Earth. His book in the 80s was called Space Colonization and the Human Condition. No, Interstellar Migration and the Human Condition. And he wrote that, and he brought in, he's an anthropologist at Hawaii, he brought in a few anthropologists and a lot of other people from the hard sciences, and they started looking at these issues. Well, a lot of that had to be updated. But one of the things that he did is he made an example of the colonization of Polynesia. On the order of 3,000 years ago, you see people beginning to move out into these places that were previously, or even at that time, are not at all the place for a large hairless primate out on the open ocean. And they do it with things like star path navigation. They devise ways of navigating simply by using the stars. And of course, when the Europeans arrived there, they're astounded that in fact they took the native navigators on board because their methods were so good. They took native navigators on board to show them where to go. Well, they had figured out that you can time the transit arc of a navigation star, and you build a star path by simply, if you want to go to that island, you memorize, there's not even a written record, there's no writing. You memorize which stars are going to rise at which time, and just as they're coming up on the horizon, you point towards those stars. And in fact, oh, well, I can't get too far into it, but you get the idea. They have devised all kinds of things. Here's a close-up of this star path navigation. Just briefly, a misconception of these vessels or this colonization is that it was particularly low-tech. And when you read the Spanish accounts of arrival in the Pacific, they refer to these vessels as canoes, and people still call them sailing canoes because it looks like two canoes lashed together. You see it in profile here, but two big canoes lashed together. But if you go to Polynesia, you find that, of course, they are not simply canoes. These are lashed together. They have enormous masts. They have enormous sails. They're outfitted for dozens of days, if not months, actually multiple months. They have a tonnage and they have a size, and if you look at them in silhouette, that make them comparable to the European ships. They weren't low-tech any more than the Captain Cook's vessel was low-tech. They're wooden sailing vessels. So getting away from the term sailing canoe is a particularly, I think, important thing. Anyway, they have a technology. They have what we would call a primitive technology, perhaps, but it is sufficient. Here are pieces of stone ground into adzes for woodworking, shells ground into adzes for woodworking. So there's a technological element early on. There is also, and this is particularly important, there's also a cultural element to this capacity for humans to adapt to pretty much anywhere they want to go. And I think Dr. Zubrin made a great point in one of his books, I think concluding one of his books, pointing out that without the will to use the technology, it's not going anywhere. Yeah? A 747 sitting on the tarmac isn't going anywhere without the human will. And so there's got to be a strong cultural ethos or interest in doing this kind of thing. Here is a Hawaiian elite, and he has his face tattooed, and this indicates his high social rank. One of the motivators for movement, to move, why did they keep moving? They have a beautiful island, they can stay there and survive. Why pick up and continually move and find these widely spread islands across the entire Pacific? It's believed that one of the motivators is found in their laws of inheritance. Traditionally, the first son of a chief would inherit essentially everything, and the second and further down the line sons inherit nothing. If they wish to prosper and build their own power and build their own chiefdoms, they must go elsewhere. And there is a cultural motivator to get up and go. And at first they go to the other side of the island, and then that becomes crowded, and then they have to keep going. So there's a cultural motivation that's quite important. There's also a great legend of a brother and sister explorer, Ru and Hina. They, having explored this in the legend, having explored the entire ocean and found every scrap of land out there, they thought, what shall we explore next? And they see the light in the sky, and they see the moon, and they actually think of it as a physical object. They don't think it's just a light in the sky. And in the legend, they build a special sailing vessel, and they go up and they explore the moon. And that's the kind of thing that Polynesians are, in traditional society, telling their children. that creates or that cultivates an exploration ethos. So there's a cultural element too, as well as the technology, and I think even more important than the technology. The Arctic, same thing, technologies. Here on the one side, on the left, is a standard harpoon. It goes straight into the tissues, and of course it prevents pulling out. So you've apprehended this sea mammal. But it can rip out if it thrashes too hard. So they invented on the right what's called a toggling harpoon, and it's just like a toggling bolt. It's shaped such that when it goes through those outer tissues, it turns sideways. It dives sideways in the tissues, and is much, much harder to pull out. That's a specific invention that was invented about 1,800 years ago by what are called the Thule people in the high Arctic, and it made whale or sea mammal subsistence, a very specialized subsistence on sea mammals possible. And that's what allowed them to go across the ice, which we now think of as the Northwest Passage, pushing east from Alaska towards Greenland, the Thule migration. It wasn't possible without those little bits of bone, slate, antler, and sinew lashed together, and somebody invented it, of course. And they also have their social motivators and their social adaptations. One is the suicide ethos, and this was essentially that when a person becomes so debilitated, their life can be difficult because resources are scattered widely. But like most foragers, they're not barely making it. They're not thinking of themselves as poor, impoverished people. Sometimes, yes, they have famine, but as long as they keep their population in line with what the resources could provide, things were all right. But sometimes somebody becomes injured, or they become so old and unable to materially contribute that they would make it. It wouldn't be a big tragedy. It was a formalized event, but it's not a big tragedy. But this is it. You say goodbye to everybody and you walk away. And that's a cultural adaptation to the physical environment, because that person, of course, elders were valued for the knowledge, the encyclopedic knowledge they have that helps people to survive. But at some point, sometimes, or a young man who gets so badly injured that he can't do anything, at some point, sometimes there was this ethos that you would remove yourself such that everyone else is bettered. Well, we're going to have, I think, both of those, technologically, of course, and cultural motivators. And so this is what I'm calling, or these are some of the mechanisms that we'll use for, I think, what I think of now as an extraterrestrial adaptation. And I'm starting now to outline the principles of what is going to, what that adaptation will entail. For example, one thing we can learn from the evolutionary process is that adaptation occurs in new ecological niches. You really need, for the processes of speciation, you need a new, or adaptation, you need a new selective environment, and then there is variation goes into that environment, and some of it makes it as successful, and some of it doesn't. Well, commonly when people think of space environments, general public now, of course, thinks of it as people orbiting Earth endlessly on the space station. Well, of course, there are bodies out there. There are, of course, the Lagrangian points. There are asteroids. There are all kinds of environments out there. There are all kinds of places with all of their own properties. And one of the things that I do to communicate when I'm talking about this kind of thing with my students, try to communicate that it's not just space. It's not just space. There are innumerable sub-habitats of space. And again, Dr. Stoker was just mentioning these caverns in Mars. Well, they'll have different properties, of course, than the surface. So to write it off, and as people often do, and I'm sure you've all encountered this, and you talk about your enthusiasm for Mars, and people will say, oh, it's just space, this is crazy. And, well, they're writing off the fact that there's variation out there, that there's variation in these different habitats. One of the things I'm outlining is essential selective agents that are going to shape human technological and biological evolution as we go along. And these are, of course, the pressures. Well, humanity has evolved for the last couple million years at pretty much at the 1 bar, 14.7 psi at sea level. We've gone up to about 18, 20,000 feet. Some populations live continuously at about 10,000 feet, and their genetics are slightly different, and their blood supply is slightly different. but it's pretty minor. It's pretty minor. Well, I shouldn't say that. It's pretty minor in the adult, but in the developing embryo, slight variations in atmospheric pressure can interfere with embryo development. And if you think about the different pressure composition or the different pressure that you might have in space environments, whatever habitat you build in that crater or in an orbiting vehicle or something, slightly different pressures based on engineering concerns, now you are also affecting or have to start to consider development of the embryo. I just saw a book in the other room here called Sex in Space. What do sperm and egg do under, let's say, microgravity? Of course, you don't have to be in microgravity. You could be on a planet. But it's not going to have precisely the same gravity as Earth. And tiny variations in that gravity could make all the difference. So natural selection is going to return for a while until we find a way to offset it with all the buffers that we've used. We'll have natural selection again. I'm writing a lot about that today. Gas composition, well, of course, different compositions than what we typically breathe here on Earth are going to be encountered also for engineering purposes. And that'll affect development. And I'm particularly interested when people think of, when I talk about natural selection in space and in the human future, people often think that I'm talking about what we think about in very dramatic terms, adults being hit by radiation or adults being, dying from eating a Mars bug. Yes, that kind of thing will happen, but I think much more, well, I guess equally important, but we mustn't forget that some of the most delicate periods of life are in gastrulation, the early formation, the early cell division, and the early assembly of that life form. That's delicate. And we don't know yet anything, really, about how that works in different microgravity, pressure, gas composition, and so on environments. So all of that has to be considered. I'll move on here. Are we about halfway through? My clock, my watch is running a bit slow. About halfway. Thank you. A large survey of evolutionary processes or the products of evolutionary processes, again, this can give you some guidelines. What's happened in the evolutionary process and what can we learn from them? Well, one of them is that if you're looking at longevity, sheer longevity in evolution, as I mentioned, most genera about 20 million years. Well, we're the genus Homo. We've been around about 2.5 million years, 2.5. Of course, this isn't written in stone. This is a statistical pattern, and of course, and this is where it gets really tricky. Humans evolve in ways very different in some cases than other life forms. For example, I'll mention at the very end that we are proactive and we are not simply reactive. Other life forms don't even know that they're undergoing the process of evolution. Well, we know that now, and we proactively alter things for our own benefit. Most species, we have, our species dates to on the order of 100,000 years, some say about 200,000. But by 100,000 years ago, people are saying we're into Homo sapiens. So about 100,000 years. Well, long-lived life forms, of those are just some benchmarks to keep your, just to give you an idea of what's happened in the evolution of Earth life. But of those longest lived, or of the longest lived of those life forms, what are some of their properties? This is very interesting. One is that they are numerous. Okay, is humanity numerous? What are our prospects in the long term? And can we use space colonization to survive longer? Well, I would say that we're numerous. I need to come up with some sort of index, but basically I would say that we are numerous. In that it's difficult to imagine, aside from really significant catastrophe from outer space, or now people are talking about these super volcanoes, it's difficult to imagine one or two environmental changes or one or two events, let's say catastrophes, from wiping out the entire species. Now, this doesn't mean that we couldn't have it very badly for a long time after a big catastrophe. It doesn't mean that the population couldn't be reduced. But generally speaking, I think that very clearly since industrialization and then on a slower increase before that, after the invention of agriculture on the order of 10,000 years ago, yes, population has increased and I think is sufficiently widespread or dense, not just dense, but sufficiently numerous and also widespread that one single event is unlikely to knock out all of our species. I'll come back to that in just a moment with regard specifically to civilization. Here's number 2. Life forms that have survived the longest tend to have a great deal of diversity. Now, a lot of this has been identified by paleontologists looking at the fossil record, but they see genera with many different species, and they say, they identify that, of course, the ones that are most diverse have the diversity, genetically speaking, diversity is your bank account against catastrophe. It's your hedge against catastrophe. If the selective environment changes, if conditions to which your genome has evolved have suddenly changed, if your population doesn't have a pretty good variety of diversity, you're unlikely to be able to survive that change, to endure that change. So diversity is important. Well, we're looking at human diversity now with very powerful genetic tools, and we see we have quite a bit of genetic diversity. This applies less to us, though, than cultural diversity, because as I was mentioning before, it's not by our genes that we're surviving largely, although we do still undergo natural selection. It's by, in fact, I put it this way, it is rather despite our genes and despite our physical character that we survive. Because if you take our technology, clothing, number one, instantly, you take the technology away, humanity hasn't a chance, overnight, right? Even in the city park. Overnight, you'll go to hypothermia or hyperthermia if it's too hot. So our diversity, technologically and culturally, is more important. Okay, another characteristic of longest lived of the species known in fossil and genetic records now, again, is that they're widespread. And so that any local event can't wipe everything out. Well, with regard to humanity, of course, this is the doomsday scenario. This is space debris, a bolide, something like this coming out of nowhere. And this could be an extinction level event. Although even the Cambrian extinction, or about 292 million years ago, this was knocked out, I think, 85% of marine life and just about everything else. Even that didn't knock out all of life. But I don't want to just have life preserved. I think civilization is critically important, and that it should be preserved. It has all of its problems. It's got tremendous problems, and we've created many of our problems ourselves, but it's still worth preserving. The processes of science, of actually accumulating knowledge, I think these are critically important. But if you look at the history of civilizations, you see that somebody else put it, I wish I had come up with the phrase, but somebody else put it just recently, that they have roughly a failure rate of about 100%. So far. All the ancient civilizations so far have undergone at least one, if not multiple, significant crashes. Egypt, 3 major civil wars where there were centuries of total chaos. And of course, today they are a museum exhibit. Egyptian civilization is dust. And look at all of them. Those stars represent collapses. And these are significant collapses, not just a little dissolution, but a significant collapse. Thank you. And what I mean by collapse is that these were not resilient systems. They couldn't rebound. They couldn't rebound from that collapse. And so what this is telling us is that there is no guarantee that ours is necessarily immune to the processes perhaps that have knocked out 99%, as I mentioned, of other species so far. Well, if we're looking at this historical, I'll move ahead rather quickly. if we're moving ahead and looking at all of this from, again, an anthropological perspective, how do we use our knowledge of biology and evolution and so on to bring a life perspective and away from, of course, we need the engineering, but if we want to engage more people, I think they have to be shown that it is about living things, it is about life, it is about human beings, families, cultures, and communities, and so on, and not just rockets and robots. If we want to do that, there are different ways to communicate, and for example, I think there are a lot of shifts we need to make. For example, how do we talk about this? The space age, as we've known it so far, has been on the left. A human being crammed into a machine. Of course, we have to think, though, about populations. We have to move out of an exploratory mode and into an idea of populations of people. And those populations are not all space astronauts or NASA astronauts, of course. There'll be individual, there'll be families of people. There'll be communities of people. So we have to think about that. We have to think in long term as well. And if we're talking about long term survival, and I'll wrap up right now, if we're talking about long-term survival and we're thinking about how to make that more likely, and I just wanted to touch on some of the ways that we can make that more likely by understanding evolutionary processes, I believe that what we need to look at the bottom of this final slide is multi-generational thinking about human biocultural change. And I am pushing for more of perhaps I'm premature in thinking about multi-generations when we're still in some, of course, we're still doing some exploration, for example, to look at Mars, to see what's there, to see what we can do there. But this is going to take so long to do that I think we should start now. And that's why I'm writing the textbook, Principles of Extraterrestrial Anthropology. Thank you. I'll be happy to try to answer any questions. Yes. Two questions, I guess. Yes, sir.
It's kind of, I'll have an example. I think I was very interested, wonderful presentation. I was very interested in especially the comments on the development of the human mind and mentation, namely that what's really going on here with everybody in this room, anybody who's human, is that it's the mind itself. We have no choice. The mind evolves itself. We're in a great human experiment. As soon as you have the dream, you have no choice. The picture of the dream is right behind you out there. Okay?
I agree.
Yeah, and so everything is about the evolution of the mind. We have no choice but to take the next logical quantum leap of mental evolution, because it will make us brighter, better, cosmically improved. And it will happen so quickly if we're standing on that surface, and we have no choice but to go there, because the mind has already taken us there. H.G. Wells took us there 113 years ago.
That all sounds great to me. And very specifically.
All is a question. Isn't this the evolution of the mind?
Yes. Just very specifically, and I'll be very brief. I would suggest look up the work of Merlin Donald, and he's writing now about how modern human cognition is in fact being changed, how our memory systems are being changed by the distribution of knowledge with internet. And it's very interesting, and it's very specific. It's not fuzzy. Yes. Sorry.
We have